So if they give you a slope field and then the y equation, that's what you're looking for. So when you see y equals 1, that's a horizontal line. You should be looking for a slope field that looks like a horizontal line. Now remember, whenever we talk about, you say, well, why would there be, so that's what, D? So 1, 7 would be D. Okay? Now you say, but if it's y equals 1, why would there be slopes up here, right? But remember, when you solve, remember when you get your original equation, it's just one possible branch depending on an initial condition, right? And so if you're given a differential equation, the y equation, the solution would have a plus c. There'd be some vertical shift to it, right? And so with some initial condition, it would narrow down. So if it was a constant function, then you would just have, there'd be some plus c. So y equals 1 would be just one of the possible solutions, okay, that are horizontal lines. What would have been the y prime equation? What would be a differential equation? What would be a differential equation that would have y equals 1 as a solution? Y prime equals what? I think you're going the wrong way. Y prime equals what? 0. Right? I mean, because if y is a constant, then y prime, the slope would have to be 0. So kind of a trivial, I guess you might say, example of a differential equation, y prime equals 0. But that would be all the different y's that have a slope that's 0. Well, that'd be horizontal lines. Okay, anyway, that's way too much time to spend on one like this. All right, number 8, y equals x. So you'd be looking at, right, equations that go through like so. So that would be h. Number 9, y equals x squared. You'd be looking for a parabola-looking shape like C. Number 10, 1/6 x cubed. You'd be looking for something that looks like a cubic kind of a graph, probably like F. Number 11, 1 over x squared. Okay. Now you might be thinking, well, I can kind of get that by process of elimination, but which might be one of the easier ways to do that one. What do you guys have for 11? Or is it, you put what? A. Okay. It's going to have a vertical asymptote because x can't be 0. So that kind of narrows it down a little bit right there. About the only option you have would be G. Would it look like it have a vertical asymptote when x is 0? And so does A. Well, by process of elimination, you look at 14, ln x. Okay, ln x also has a vertical asymptote. Now, interesting thing on, let me switch worksheets here and look at that one. So if you look at G is going to be the last one, 14, ln x. And let's talk about that absolute value around there, because we're going to see that again. We're going to see that again later on. Because normally natural log, you cannot have put a negative into natural log. And so that's why they put the absolute value there. So here's what our normal, a normal natural log graph would kind of go up and do that, right? And you don't have anything over here. But if they give you the function like this, now you can put in negatives for x, right? Now we can put in negatives for x because this will turn positive before we do the natural log. So we could have negatives for x, and then if we were over here, if we had an initial condition over here, it would look like so. Okay. All right. What is the derivative? Well, let's just talk about why that is real quick here. What is the derivative if y is equal to ln x? This is how we've usually seen it. What's y prime? 1 over x, right? That's a derivative. Now, is there any limitation on x here? X can't be 0, but couldn't x be negative, right? Now, if we started with this function, then we know x can't be negatives, right? So if the problem started with y equals ln x like this, well, we know by natural domain or the applied domain that x can't be negative. So we would be looking at, if you were going to draw the slopes, so here's the ln x graph right here. if you were going to draw the slopes of that, right, they're going to be positive slopes and big positives to start, but then they're getting less and less and less, and then they're heading down towards almost a zero slope, but they'll never quite get to be a zero slope because this keeps increasing, but really, really flat. Okay, so this is going to come down and just do this, but there would be nothing over here, right? There would be nothing over here. Now, let's reverse that. Let's talk antiderivative here. Let's say we started with 1 over x. Let's say we started with y prime equals 1 over x. That was the problem, okay? We just started with y prime equals 1 over x. Now, could x be negative? X could be negative in that scenario. So if we're going to say, let's do the antiderivative of 1 over x, as we'll learn when we get into chapter 5, the antiderivative of 1 over x is ln absolute value of x. Because x could be negative here, but yet we can't let it be negative going into there. So we'll have to put absolute value bars around it. So the graph of 1 over x looks like this, right? So if we start with the function 1 over x, then we have this. Well, what's the antiderivative of that look like? Well, we know what ln x looks like if x is positive, but what about here, right? If these are the slopes, these are all negative, right? These guys are all negative, so that's why the other branch of this looks like this. It's decreasing the whole time because this is negative. Pretty flat, almost zero, going to really steep negative, right? Looks like that because that's what the 1 over x graph looks like, okay? So just a little bit of things to look forward to. That's why they put that in there. That's why they set those bars around, because of some stuff we're going to see later. Okay, what was 12 then? 12 would have been sine, which would have been E, I guess, and then cosine would have been whatever's left. What's cosine? This one? B. All right. Okay, quickly now, let's finish here. So this is a little more like what we're going to be doing now. Okay, so 15. Which one you got for 15? B, this one up here, because it's got only x's in it, so it's got to have columns, vertical columns, where the slopes don't change, and it'd be an x squared. You can tell that's a parabola. Okay, 16 has just a y in it. That's got to be D. That's going to be your exponential one, so you start to recognize those. That's good. 17, it's got both x and y, so it's got to be one of these two. So, pick something easy. Y is a 1. Right here, y is a 1, and x is 0. 0 minus 1, you get negative 1. Well, that doesn't have negative 1 slope, but this one does. Negative 1 right there. So just pick a point. Looks like that one works. Put 0, 1 into this one. 0 divided by 1 is 0. Yep, that one's out. That one's there. So 17 would be C. 18 would be that one. Okay, and then the other thing I'd want you to be able to do is if I give you a slope field like this, and then give you an initial condition to be able to kind of sketch in. Okay, now this isn't going to be on our next curve just because time-wise we're not going to have time, probably enough time on that to do it. If I change my mind on that, I'll let you know. We got a lot to do before our next quiz. Our next quiz probably isn't until next Friday. So 9 days, 10 days from that, school days. All right, so, and then this one, again, they give you the slope field. So it gets a little trickier when you get in these asymptotes and stuff like that, but if you put a 0, 1, this would kind of follow like so. It looks like it flattens here. Now, there's not really enough little slope segments to tell for sure, but what this one's going to do is it's just going to go like that. And it's going to be it's going to follow that asymptote like that. Okay, and this is just going to go steeper and steeper. Now, negative 3, 0, though, you get over here, this one is kind of going down, 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 and then up, up, up like that, but along the asymptote. This is just going to keep going down like so, and then you're going to have that. Okay? All right. So, anyway, that kind of rough sketches of that, but that's all right. The other worksheet, let's turn to that real quick. Just kind of want to look at the matching. Let's go down through here. So what do you have for number 1? E. 2.
C.
Unless we really disagree, we're just going to roll along here. 3.
A.
4.
G.
Number 4,
J.
J.
Yeah. G. J.
4. J? I don't think you can be J.
It's G.
I'm looking at the y-axis. When x is 0, it would have to be, the y be getting bigger and bigger, so it would have to be getting steeper and steeper, which this one is. I think it's G. Okay, 5. 5 is B, yeah. 6,
D. T.
D. 7,
K. I. I'll be I.
7 is I, we'll go to the majority. 8,
H.
H. 9, F, okay. 10,
K or A? K.
which one are we doing? 10?
You were the one who said that.
10 is K. 11,
J.
J. So what did we say? 11 is J?
Yeah.
Yeah, 11's got to be J, right? And 10's got to be K. The negative makes a difference, okay? And again, just this one right here, this point right here is enough to tell you. Right here, there it's a negative slope, there it's a positive slope, okay? So 1/2, 1/2, or call it 1, 1, doesn't matter. 1 divided by 1 is going to be 1, but this one will be negative, so the one that's negative has got to be that. All right? Okay, good enough. So, get your notes out here somewhere. We were talking about midterm review. We're going to do a little more of that today. We're not going to get started. We're going to do one more day here of just kind of, we had some people gone. I know in the other classmates too have gone Thursday and Friday with this stuff, so that's good. Before we jump into the quiz stuff, we get back into chapter 4 specifically on the things that will be on our next quiz. Kind of want to do a little more of this midterm review. Then we're going to focus really on chapter 4 stuff for the next 2 weeks pretty hard, leading up to that next quiz, and then we'll start mixing in kind of some review and some, and then finish in chapter 4. So what I have up here right now is last year's. This is the one that Kearney High students took. AP test, the free response questions. Okay, so what I thought we'd do here to start today is just kind of go through, there's 6 free response questions, go through and see what we've already learned, and obviously what we have yet to learn, and see how we can do on them. Give you a little bit of time to work with each other. So here's number 1. Okay, now this graphing calculator is required for these questions. That doesn't mean you have to use it for all parts of these questions. Okay, now let's look at number 1. Okay, so we cannot do any parts of number 1. Okay, just looking through it. Okay, what it gives you is a tank that's 10 feet high. It gives you the square feet of a slice of a horizontal cross section of the tank. It's not just a cylinder type tank. Okay, and it gives you that at various things. Ask you questions about it. That stuff we have yet to learn. Okay, all right, moving on. And again, you can use a calculator for this part as well. Okay? I know we can do part B. And we can do part C, and that's it. So go ahead and try it. do parts B and C, and you can use your calculator, but still write down, just like you would on any free response question, what it is you're doing, and or plugging into your calculator, whatever. For part C, you got to really pay attention. Well, even in part B, you got to really pay attention to the units that you're given in the problem. What are the units on F? Okay, so let me unfreeze this. All right, so here's what the scoring guidelines look for the test. So negative 8.120, is that what you said? 119?
1195.
Okay, so either one is okay, and so you got 2 points on that question for having the right value, and then giving the meaning, and so you would need to say something like this, because it said in context of the problem. So this would be bananas, or pounds per hour, right? I guess you could say per hour squared. But, and also notice it talks about They said decreasing, so they took the negative off. So it says that the rate at which bananas are being removed from the display is decreasing. So the rate is decreasing. So, right, that's concavity. That's acceleration, if you will. That's pounds per hour per hour. Okay, so the rate that they're being removed, because that's what F is the rate they're being removed in pounds per hour. So that rate is decreasing. Okay, because think of the chart. This would be like your second derivative. So what we're talking about here is we're really talking about F being, this is what's going to help us on the next one. F is pounds per hour. So F prime would be pounds per hour squared. And so it'd be like big F up here would be pounds, right? So we're thinking of the chart. F prime in this case, when F is decreasing, that's pounds per hour, okay? F prime would be negative, which we just got there. Okay, so anyway, 2 points there. Did anybody get anything for part C? Let me ask you this. Did you have to use both F and G? You did. You did, okay? Because here's the thing. F, so bananas are being removed from the table, and then as it starts getting low, so think about it in the store, so it started at, I can't remember now at what time, but it says, so bananas are being removed from the table, right? And so it starts getting low, so the workers start putting bananas on at a certain rate, So now what you have is bananas getting put on the table, and at the same time, customers are taking bananas off. So the pounds of bananas on the table is going to be, or the rate that they're coming off is going to be G minus F. G is putting on, so that's a positive, and F is taking off, and so you have to subtract. And that's going to be pounds per hour. So it says, is the pounds of bananas increasing or decreasing? So think about what I just had up there a minute ago. This is where you got to think about units. Now, a question like this is going to be much easier for us later in the year. When it's time for us to take the AP test, I don't think this will be hard at all. This is the first time you've seen this kind of thing. We're going to talk a lot about this kind of application of the derivative and so forth, okay? But in this scenario, F is pounds per hour, okay? And so is G. So when the question, I guess I need to go to the, I don't know why I have this covered up. Okay, if we go to the question, all right, is the number of pounds increasing or decreasing at time t equals 5? Okay, so again, my thought process on that is going to be, this is why I said thinking of units. If I'm thinking of the chart, I got pounds per hour here. Is the number of pounds on the table increasing? The question to me then becomes this. If pounds is increasing, that means F, well in this case G minus F, but my pounds per hour would need to be negative. Or excuse me, that's positive, right? Is it increasing or decreasing? So if it's decreasing, then that's going to be negative, right? So I have to think, okay, so what's pounds per hour in this problem? Well, F and G both are. G is bananas going on, F is bananas coming off. So G minus F would give me the pounds per hour at 5. And so all I have to do is take my calculator, plug a 5 into G, plug a 5 into F, and I get this. And since that's negative, the pounds are decreasing. Okay? So really there wasn't much math to do there. It was understanding the units and understanding the idea of the chart, because with your calculator, it's really easy to just plug a 5 into those two equations. You didn't have to do anything. Okay, so it's just understanding what we need to do with those. Okay, let's move on. So a lot of our review for the midterm, and then as we go on later into the year before the AP test, is just recognizing these different types of problems. Right? But it's really good because, I think in most math classes, I'll be real honest with you, most math classes, you go through the book, you go through the section, you learn the what to do to manipulate the numbers and things, and you do some story problems, some applications, some things along the way, which is good. But one of the things that kind of us preparing for the AP test, what I like about the AP test, I think they do a really good job of asking questions in a lot of different ways that make you really use and think about the things we've learned all year long and put it together and tie it together. And then along the way, we also have to review trig, and we have to review, all kinds of algebra concepts too. I just think it's really good. I really think it's not the funnest part of what we do all year, I'm sure, but when we do these big packets and we review for our midterm and we review for our AP test, I really think it's probably the best thing in your entire math career at Kearney High for your long-term processing and learning of these concepts for you to take forward in whatever math class you have to take in college. I really think it is a way, kind of capstone way to put this all together. So hopefully you'll see it that same way when we get to the end of all this at the end of the year. Which always drives me nuts when somebody decides to take it easy fourth term and drop the calc with a B at the end of third term. Like, the best part is still to count. Anyway, all right. Number 3. No calculator is allowed here. Okay, so here is an equation. And this is, notice it said this is a graph of f prime. Probably can't do A. We can do B. Probably not C. For right now, it would be a lot easier later. But D we can. So B and D, do those, and those will teach you. B and D. All right. Oops. So, where is F increasing? From that's 5, right? Piece of cake, right? After did it say? It did say justify your answer. What would you say? Positive, right? F prime is positive. So simple as it gets, chart kind of question. There's F prime. Wherever it's positive, above the x, just say F prime is positive on that interval, and that's it. Okay, probably a couple of points. Let's see what it said here. 2 points, yeah, your answer and then justification. Now notice they use closed. It said it's positive, and they used a closed interval. Here, increasing, they used a closed interval. It doesn't matter, the closed open. They've made a real point of telling us that when you're doing chart stuff, where's a concave up, concave down, increasing, decreasing, that kind of stuff, open, closed interval, either way is going to be fine.
Okay, all right, -1/2. Okay, so let's go back to the other one. So at f double prime of -5, isn't that just a slope here? -1/2, right? It's a line, and so actually it'd be back here, and so it's just -1/2, right? And then f double prime at 3. What'd you say? Does not exist. Explain why. Sharp point. I would say for right now, I think that's going to be okay. They went through, you may have seen it here, they went through a whole kind of strange explanation. Their explanation uses not our normal slope formula. We do f of a plus h minus f of a all over h, and this is an alternate version, if you remember, that we did this. But they talked about the left and the right. And that's why, because the limit, the slope on the left is different than the slope on the right. Okay, so when you have a smooth transition, not a sharp point, then the slope on this side is approaching the slope on this side, and where they meet, that's the slope. Okay, the reason you have a sharp, the reason the slope doesn't exist at a sharp point is because the slope on this side is whatever. What is that? 2/1. So the slope on this side is 2, and the slope on this side is -1, and they don't meet. And then so this side. So the slope on the left is different than the slope on the right as you approach 3. So that wouldn't be a bad thing. As we get later in the year, we might clean that up a little bit in what we say. Okay, but for right now, I think there's a sharp point there. The derivative does not exist at a sharp point. Okay, let's go on to this one. All right, so we've been talking about differential equations, slope fields a little bit. A boiled potato is taken from a pot on a hot stove, left to cool in the kitchen. The internal temperature of the potato is 91 degrees at time 0. And it's greater than 27 for all times, t greater than 0. The internal temperature can be modeled by the function h. So h is the temperature. So it's always important in these problems to think about your degrees, your units, because again, a lot of times this always comes back to the chart, right? I mean, this is degrees Celsius. So right here, the temperature of the potato is modeled by the function h. So h is going to be degrees Celsius, so therefore h prime, which is this, right? And there's a differential equation, and notice it's got h in it, not t. So that's kind of like having your y in it, right? This is not one we could just do, we could solve by doing, say, an antiderivative. H is measured in degrees, it says it again right there. So this would be degrees Celsius per minute. Our time, t, somewhere, I think it says, is minutes, doesn't it? Right there, minutes. Okay? So h prime is going to be degrees per minute. Okay, so we can do part A, I think, or we can at least get the beginning of part A. We can do part B, and I'll give you a hint. Think implicit differentiation. Okay, what does this mean when you see this? Second derivative. This just means h double prime. This just means h double prime. Okay, that just means h double prime is all that means. Okay, now these are going to be a little tricky, but you can at least get the start of it, I think. So h double prime. Well, if you're going to do h double prime, this is h prime. You have to do the derivative of that. But it's kind of like we said with implicit differentiation. Everywhere you see a y, you do the derivative. You tack on a y prime, right? Well, it's going to be the same thing here with an h. You tack on an h prime. Okay, so it's an implicit differentiation. Okay, so let's see what you can think about on those two here. We have enough knowledge at this point to do A and B. Just haven't seen anything quite like it yet. Okay, so see what you can do. Give it about 5 minutes here. 5 or 10. Remember, to write a tangent line, you need a point and a slope. Point and a slope. And this is a no calculator, by the way. No calculator. All right, let's talk about a couple of parts to this. Okay, so right away, we have a differential equation, and again, all those things that are important about this problem that I already told you about how, think of the chart, think of H prime, these interconnections, think about what the units of each thing are. I think those are critically important to helping you do and know what to do in the problem. So it says, write the equation of tangent line, the graph H at t equals 0. So anytime it says that, write the equation of tangent line, you need a point and a slope, right? What's the point going to be? H of 0 equals 91. And the slope will be H prime of 0, right? Equals what? What'd you get? Negative 16. How do you get negative 16? Well, here's H prime right here, right? This is H prime. So how are you going to find H prime of 0? You're going to plug a 0 in to H prime. Oh, but you can't plug a 0 in because that's little t, and there is no little t, but there is a big H. So when t is 0, what's big H? 91. So 91, so you put a 91 in for H. Okay? So you're finding H prime of 0, but there's no 0, there's no little t to plug the 0 into, but you can plug the 91 in. Okay, 91 minus 27 is 64. You can do that without a calculator. Times 1/4, they make it work out nice. Negative 1/4, that's negative 16. Okay, so that gives you a point and a slope. So that allows us to write an equation of a tangent line. Now, I think if you used y and x here, they'd probably let you do that, but it's actually h and t are really our variables. So if you use y and x, probably okay, but we should use h and t. So we just put our slope and our point right there. So that's the tangent line. So you probably got a couple points for doing that. Use this equation to approximate the internal temperature of the potato at time t equals 3. So what would you do at that 3? Plug it in to the tangent line equation right here. So you put a 3 in there, negative 16 times 3 is negative 48 plus, because basically what this means is the potato is cooling 16 degrees every second, right? So it was 91, goes down 16, goes down 16, goes down 16, right? Goes down 48 degrees. So that gives you a temperature of 43 degrees. Now, is it really going down 16 degrees every second? No, right? Now, okay, and again, there's some really important concepts here we're just really talking about for the first time. So understand, this is going to get easier and easier over time. Okay, but what we're doing is we're taking, so everything so far we've done, we've talked about before, right? Just never really quite in this context of this problem, okay? But we're putting it to good use to do something that might be useful. All right, so, because what does that mean if it goes down 16 degrees every second? That the potato is cooling in what sort of fashion? A linear fashion, right? But is it really? No, it's changing all the time. The slope is changing with every degree or part of a degree that H changes, the temperature of the potato, right? So we're making a big assumption here. So let's say that the thing is cooling and so the temperature of the potato is going down like that. What we did is we found this tangent line at 0, and we estimated way out here here's 0, here's way out here at 3, we estimated on our tangent line that the temperature would be that, right? But really the temperature could be what? Temperature could be a lot lower. Or what if the potato was coming down like this as it cooled? Then we found the tangent line here. So right here at 0, we found this tangent line, and we went way out here to 3, and we said, well, the potato is this temperature. But really the temperature could be more. Well, I've kind of led you into part B now, haven't I? Okay? Part B said, use H double prime to determine whether your answer in part A is an over or underestimate. Well, see the two examples I just gave you? If our tangent line is up here, then our estimate is an overestimate of the temperature. And if the tangent line is like this, then our answer is an underestimate of the temperature, right? And what determines whether our answer was over or under? The concavity of the H curve, right? If it's concave down, our tangent line will be above. If it's concave up, our tangent line is going to be below. Well, what measures concavity? H double prime, right? So they were kind of leading you to it even in their question. They said, use H double prime to determine whether your answer. So, I've started that here. H double prime would be just do the derivative of this. Well, actually you could simplify this. This is negative 1/4 H plus 27/4, right? I can just distribute that. That's H prime. So now what's H double prime? Well, H double prime would just be negative, what's the derivative of negative 1/4 H? It's negative 1/4, tack on a H prime. And then the derivative of 27/4 would just be 0, just go away. Implicit differentiation. Here's a great example of where we need it. Okay? So here's H double prime right here. Well, what do we know H prime is? No.
No, it's negative, but like...
It's degrees per minute. What's our degrees doing in this potato? It's cooling. So H is... Don't we know H is decreasing? Isn't H decreasing in this problem all the time? So H prime's got to be negative all the time. H is decreasing, so H prime's got to always be negative. So if H prime is always negative, what's H double prime? H double prime's got to be positive, which means H is concave up. So which one of my two situations do we have? We have that one. So the potato is coming, the temperature of the potato is coming down and it's leveling off like so. Well, Newton's law of cooling, we kind of talked about that a little bit, right?
but it's coming down and it's leveling off. It's a concave up situation. We showed it there. And we have to say that. We can't say Newton's law of cooling. They said use H double prime. So you got to show this, right? And then, so we just showed that H double prime is positive, so therefore H is concave up. Since H is concave up, the tangent line will be below the curve, and so our approximation in part A is an underestimate. That's what we've been saying. Yes, sir.
See how you use H double prime, you can't just say that you know it's cooling out.
Like Newton's law of cooling kind of thing. Right. Because of use H double prime, right? Because of the, and they're real careful in their wording when they, how they want you to do that. Okay, so let's just look at how they allotted points for that. Equation tangent line, okay, which is what we asked. So they had 3 points for that. One for figuring out the slope. So if you on your paper had rightfully plugged in a 91, if you got the negative 16 and they could find that on your paper that you had done that, then you're going to get a point for that. Even if you couldn't figure out how to get the tangent line equation. Notice they did use y, and they used t. But so they're pretty lenient on that, some types of tangent lines especially. And then getting your approximation of 43. Then right here they got their second derivative, which is the way I had it. So we got a positive value. So they went ahead and they said, so h is greater than 27. Well, that was, they actually plugged it back into that differential equation and said the temperature of the table is always going to stay above 27. Okay, so they plugged numbers in. But basically what we said, it's concave up. Since the graph's concave up, the answer is an underestimate. So what's interesting, you only have 1 point for that. A lot of figuring in there, not figuring, but understanding it. But you just got 1 point, which I guess makes sense because it's almost like a yes or no question. It's under or over, so there's not a lot going on there. Okay, let's move along here. Just got time. Let's see. There's 2 more. Let me see. What would be better? Let's do this one. Okay, this is no calculator. This one we can do. This is 2 particles move along the x-axis. The position of particle P is this one. So x, this x function of P, that's the position function. And this is the velocity function of particle Q. Okay, and they tell you particle Q is at this position at time 0. Okay, so we should be able to do A. We should be able to do B. We should be able to do C. Should be able to do all 4 of those actually. Okay? No calculator. Remember that a fraction equals 0 when the top is 0. A fraction equals 0 when the top is 0. Little hint on number 1. Okay, I'm gonna hand out a packet here and give you some work time, so I'm gonna let you keep working on this, but let's just talk through real quickly the process on each of the parts, because I know some of you are gonna be at different places here. So when is P moving to the left? What are you gonna do there?
So it's the velocity of the two,
How do you get the velocity?
do the derivative.
Derivative of this, right? So you have 1 over the inside times the derivative of the inside. That's why you'll have a fraction I was talking about. Okay, so set that equals 0, which would be when the top is 0. I think it comes out 1. Is that right? T equals 1. Then do a number line. Okay. Where are the two particles going in the same direction? So you know when this is moving left and right, and so now you just got to do the same thing for Q, but you already have a velocity on that, right? So you just set that equal to 0, right? You already got the velocity for Q right here. So set that equal to 0, see when it stops, do a number line for it. So you have a number line for Q, and then do the derivative on this, and have a number line for that, and then you can tell when they're going the same direction. Find the acceleration of Q at time 2. So you're going to need what here? And you may not have gotten this far yet, but you're just going to have the derivative, right? Give you the acceleration at 2. Is the speed increasing, decreasing, or neither? That's speeding up or slowing down, right? Because they use the word speed. So is it speeding up or slowing down? What do you need to do speeding up or slowing down? Acceleration and velocity. We just found the acceleration at 2. Now you need the velocity at 2. Well, you already got the velocity equation up here for Q, so you can get that. Find the position of Q the first time it changes directions. Q, that's this one. So how do you get position?
Find the position function.
How do you get the position function?
Antiderivative.
Antiderivative, you're going to have a plus C. Do you have an initial condition? Do you get the C? Do we know something about Q right here? We know the position of Q right here. We have an initial condition. So we can find the C. So we can get the position function, and then the first time it changed direction, we already found that, I think. Where would you have found the first time Q changes direction? Did you get that in part B? When you did your number line, right? Or you do a number line for P here, you're going to do a number line for Q here. That's going to tell you when it stops, which direction it's going. So the number line you did up here in B should tell you when it changed direction, when Q changed direction. So you're going to know when that is. So once you get your position function, then you can take that value, plug it in. Okay, a little later I'll put up my answers that I have for this so you can check that. Okay, our homework for tomorrow is going to be in this first of our midterm review packets. I 3-hole punched them if that helps you out. If you just have a folder to stick in, that's fine too. But and what we're going to do, what I want you to do as part of your assignment is to attempt to the best of your ability in the first section. So, okay, so if everybody will just pause for a second, look at the packet. So this is just like an AP test. Now this is from an older version. A couple years ago they changed the AP test to be 30 no calculator problems in the first section, and then 15 calculator problems in the next section, the 2 multiple choice sections. The old version was 28 and 17. So that's what we have here. But so basically the first 28 questions takes you up through page 13. Okay? Those are the no calculator multiple choice problems. Now only do the circle, so it's not 28 problems. Okay, it's about half that. I haven't counted, but I'm assuming it's about half that. So it's about 14 problems. And if this was a timed, you would have about 2 minutes per problem. So you'd have about 30 minutes to get it done. So it shouldn't be any more than 30 minutes over, but it may take you longer. Now, some of you may not be able to do. Tomorrow we'll start class with, I will take some questions on the 1 through 28 if you got something you were just stuck and we're sure what to do. Some will seem pretty easy, some will be like, ooh, I haven't seen that before. Okay? But we should be able to do. Well, I take it back. We still have a few sections in chapter 4 to do, right, before we're ready for the midterm. So every once in a while we might run into a problem like, oh, we haven't learned that yet, we'll learn that next week. And that may happen too. Okay? So do the best you can on the circled ones through number 28. Okay? All right. So go ahead and keep working, finish this one, then you can start working on your packet here. And I'll throw the answers up to this here after I give everybody a chance to get. Okay.
Okay, I put the answers up. Don't look if you don't want to see them yet. I think, and I just worked those kind of quickly, so I think they're correct.